Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will see that how to represent any Boolean function or the Boolean expression in a sum of product and the product of sum form. And we will also understand the concept of Minterms and the Maxterms. So we know that in the digital electronics, if we have any logic circuit, then its output is the function of the digital inputs. And the relationship between the input and output can be represented either using the truth table or using the Boolean expression. So from the truth table, we can understand that for what input combinations, the output of the logic circuit is high. And the same thing can also be represented using the Boolean expression. Now this Boolean expression or the Boolean function can be represented either in the sum of product form or in the product of sum form. So first, let us see the sum of product form of representation. So in this SOP form, the product term is the logical AND operation of the different input variables, where the variables could be in the true form or in the complemented form. So these are the few examples of the product term. So in this A dot B, both the variables are in the true form, while in the second case, these A and C are in the true form, while the B is in the complemented form. Similarly, in the third case, this A is in the true form, while the B is in the complemented form. Now in this SOP, this sum refers to the logical OR operation. So in this sum of product form of expression, different product terms are logically ORed. And this logical OR operation is represented using this plus sign, while these terms are the product terms. So let us see some expressions which are in the sum of product form. So if you see this function f1, then it is in the sum of product form, because here this A can be represented as A dot A. So if you see all these three terms, then they are the product terms, and this plus sign represents the logical OR operation. Similarly, let's say this f2 is the function of variable A and B, and this function is also in the SOP form. Now the expression in this SOP form can be in the canonical form or in the non-canonical form. So in this non-canonical SOP form, each product term may or may not contain all the variables of the function. For example, this first expression is in the non-canonical form. So if you see this expression f1, then it is the function of the three variables. But if you see this first product term, then it contains only one variable. While if you see this second and third term, then they contains only two variables. That means each product term does not contain all the variables of the function. Therefore, this expression is in the non-canonical form. On the other hand, in the canonical SOP form, each product term contains all the variables of the function, where the variables in each product term can be in the true form or in the complemented form. So this second expression is in the canonical form, because here each product term contains all the variables of the function. Similarly, if you see this function f3, then it is also in the canonical SOP form, because here this f3 is the function of three variables, and here each product term contains all the variables of the function. Therefore, this expression is in the canonical SOP form. So in short, the sum of product form of expression can be categorized in the two types, that is canonical SOP form and the non-canonical SOP form. Similarly, now let us see the second type of representation, which is known as the product of sum. So as I mentioned earlier, this sum refers to the logical OR operation, while this product refers to the logical AND operation. So in this POS form of representation, this sum term is the logical OR operation of the different variables, where each variable could be in the true form or in the complemented form. So these are the few examples of the sum terms. So in this product of sum or the POS form of representation, different sum terms are logically ANDed. So this dot represents the product or the logical AND operation, while this term inside the bracket represents the sum terms. So that is the product of sum form of representation. So now let us see few more expressions which are in the product of sum form. So here, this function f1 and f2 represents the Boolean expression in the POS form. So as you can see, each expression contains the sum terms and these terms are logically ANDed. Now, similar to the SOP form, this product of some form of expression can be categorized in two types, that is canonical and the non-canonical. So in non-canonical type of POS form, each sum term may or may not contain all the variables of the function. For example, this F1 and F2 are non-canonical form of expressions, because if you see this F1, then it is the function of 3 variables. But if you see the first sum term, then it contains only 2 variables. Similarly, this last term is also missing the variable a. Similarly, if you see this F2, then it is the function of 4 variables. But if you see each sum term, then it does not contain all 4 variables. Therefore, these two expressions are in non-canonical POS form. On the other hand, in the canonical POS form of expression, each sum term contains all the variables of the function. So if you see this function f3, then it is in the canonical POS form, because here each sum term contains all the variables of the function. So these variables could be in the true form or in the complemented form. So similarly, if you see these functions f4 and f5, then they are also in the canonical POS form. So in short, this product of some form of representation can be of two types, that is canonical and the non-canonical. Now if we just talk about the canonical form of representation, then in the canonical SOP form, each product term is also called Minterm, and therefore this canonical SOP form of representation is also said to be a sum of minterms. Similarly, in the canonical POS form of representation, each sum term is also called Maxterm, and this canonical POS form of representation is also said to be a product of Maxterms. So first, let us understand what is this Minterm and the Maxterm, and let us start with the Minterm. So this Minterm is the product term which consists of all the variables of the function either in the true form or in the complemented form. So now let us see, if we have some function of n variables, then what are the possible minterms of that function? And if we have been given the truth table of some logic circuit, then how we can write its Boolean expression in the form of minterms? So if we have some function with the two variables a and b, then there are total 4 different possible input combinations, and following are the minterms corresponding to each combination. So now let us see how to write these minterms. So in the particular combination, if the value of that variable is 0, then in the minterm expression, it can be written in the complemented form. And if the value of that variable is 1, then in the minterm expression, it is written in the true form. For example, in this first case, the value of the both variables a and b is 0, and therefore they are written in the complemented form. While in the second case, this a is 0 while this b is 1. Therefore, this a is written in the complemented form while this b is written in the true form. Similarly, in the third case, this minterm is equal to ab bar, and in the fourth case, this minterm is equal to a dot b. So that is how we can write all the minterms according to the input combination. Now for convenience, these minterms are also represented by the lowercase letter m followed by the number, which is decimal equivalent of the input combination. That means this 00 corresponds to m0, while this 01 corresponds to m1. Likewise, this 10 corresponds to m2 and this 11 corresponds to m3. Similarly, for the 3 variables, following are the minterms. Now, since the minterms are the product terms, so its output is 1 only for the specific input combination. For example, this minterm a bar dot b bar dot c bar is 1 when all the inputs are 0. Likewise, this minterm m3 is 1 when the input a is equal to 0 and the input b and c are 1. And likewise, the output of each minterm is 1 only for the specific input combination. So as you can see, for the 3 input variables, there are total 8 minterms. Or in general, for the n input variables, we have total 2 to the power n minterms. So now let us see, if we have been given the truth table of some logic circuit, then how to write its Boolean expression in the form of Minterms. So as you can see, this f1 is the function of three variables a, b and c. And this function f1 is 1 only for the specific input combinations. Now if you want to write this function f1 in the algebraic form, then what we will do? We will write down all the minterms corresponding to those combinations for which the output of this function is equal to 1. And then we will logically OR all these terms. And if you see this function f1, then it is in the canonical SOP form. Or we can say that it is the sum of minterms. Alternatively, we can also write this expression as m0 plus m2 plus m4 plus m7. Because as we have seen, this a bar dot b bar dot c bar is equal to m0, while this a bar dot b dot c bar is equal to m2. Likewise, this a dot b dot c corresponds to m7, while this a dot b bar dot c bar corresponds to m4. That means alternatively, we can also write this expression like this. And further, in the more abbreviated form, it can also be written like this. So here, this sigma represents the summation of minterms, and these decimal numbers are the subscript of these minterms. So all these three expressions of the f1 are in the canonical SOP form. So similarly, let us take one more example. So here, this function f2 is 1 only for the three input combinations. So first, let us write down the minterms corresponding to those input combinations. And then, let us perform the logical OR operation of these minterms. So further, this function f2 can be written in this form, where this m1 is equal to a bar dot b bar dot c, while this m4 is equal to a dot b bar dot c bar, and this m6 corresponds to a dot b dot c bar. And in the more abbreviated form, it can also be written like this. So in this way, from the truth table, we can write the Boolean expression of the function in the form of minterms. Similarly, now let us see what is Maxterm. So if we have a function with n variables, then its Maxterm is the sum term which contains all the variables of the function, where the variables could be in the true form or in the complemented form. So for a function with n different variables, there are 2 to the power n different possible Maxterms. So let us take the case of two variables. So for the two variables a and b, there are total 4 different input combinations. And here are the Maxterms corresponding to each combination. So as you can see, each Maxterm is the summation of all the variables of the function. Now these variables can be in the true form or in the complemented form, and that depends on the value of the variable. So if the value of that variable is 0, then in the Maxterm, that variable is represented in the true form. On the other hand, if the value of that variable is 1, then in the Maxterm, it is represented in the complemented form. So as you can see, in the first case, the value of both variables a and b is 0, and therefore they are represented in the true form. Similarly, in the second case, this a is equal to 0 while b is equal to 1. So this a is represented in the true form while this b is represented in the complemented form. And the same procedure is followed for the remaining combinations. And for the convenience, these Maxterms are also represented by the uppercase letter m followed by the number, which is the decimal equivalent of the input combination. So in this case, we have Maxterms starting from m0 to m3. Similarly, for 3 variables a, b and c, following are the 8 Maxterms. So now let us see, if we have a truth table of some digital circuit, then algebraically how to write its output in the form of Maxterms. So here is the truth table of the function f1, and as you can see, the output of this function is 1 for the 4 different combinations. So first, let us find the f1 bar. Now since the f1 bar is the complement of the f1, so when f1 is equal to 0, this f1 bar will be equal to 1. So first of all, let us represent this f1 bar in the form of sum of minterms. And for that, let us do the summation of all the minterms for which this f1 bar is equal to 1. So here, this minterm corresponding to 001 is equal to a bar dot b bar dot c, while the minterm corresponding to 011 is equal to a bar dot b dot c. Likewise, the minterm corresponding to 101 is equal to a dot b bar dot c, and the minterm corresponding to 110 is equal to a dot b dot c bar. Now if we take the complement of this f1 bar, then we will get the f1, right? So using the De Morgan's law, let us simplify it. So just break this bar and give it to the individual group, and at the same time also change the sign. So once again, using the De Morgan's law, we will get the following expression, which is in the product of sum form, and here each term is the max term. Now if you closely observe, then this max term a plus b plus c bar corresponds to 0 0 1. Likewise, this max term a plus b bar plus c bar corresponds to 0 1 1. Similarly, this a bar plus b plus c bar corresponds to 1 0 1, and likewise this a bar plus b bar plus c corresponds to 1 1 0. So all these four combinations corresponds to max terms m1, m3, m5 and m6. So in a simplified form, we can also write it like this, or equivalently it can also be written like this, where this pi represents the product or the logical AND operation of all max terms, and the number inside the bracket represents the corresponding max terms. Now one more thing, if you observe, then for all these max terms, this function f1 is equal to 0. So directly from the truth table, if you want to write this expression in the POS form or in the form of product of max term, then we just need to consider the terms for which this function f1 is equal to 0. So let us take one more example so that it will get clear to you. So here is the truth table of the function f2. So if you want to write it in the form of max terms, then just consider the terms for which this function f2 is equal to 0. So these max terms are 0, 1, 6 and 7, or equivalently it can also be written like this. And if you want to represent it in the algebraic form, then we can also write it in this fashion. So in this way, directly from the truth table, we can write the function in the canonical POS form or in the product of max term. Alright, so for the three inputs A, B and C, here are the corresponding min terms and the max terms. So if we see any max term, then its output is equal to 0 only for the specific input combination. For example, this A plus B plus C is equal to 0 when all the inputs A, B and C are 0. Likewise, this A bar plus B bar plus C bar is 0 when all the inputs A, B and C are 1. Moreover, if you observe, then each min term is the complement of the corresponding max term. For example, if you take the complement of this A plus B plus C, then we will get this A bar dot B bar dot C bar. Or we can say that this M0 bar is equal to M0. So in general, we can say that these min terms are the complement of the max term. So using this, we can convert any canonical SOP form into the equivalent POS form, and vice versa, we can convert any canonical POS form into the equivalent SOP form. So let's say we have been given this function f1 and it is in the canonical SOP form, and as you can see, it is the function of 3 variables. Now if we take the complement of this f1, then it contains all the min terms for which this function f1 is equal to 0, right? That is equal to 1, 3, 5 and 6. Or we can write it as m1 plus m3 plus m5 plus m6. Now once again, if we take the complement of this f1 bar, then we will get the f1. And using the De Morgan's law, we can write it as m1 bar dot m3 bar dot m5 bar dot m6 bar. And as we have seen, these min terms are the complement of the max term. That means if we take the complement of these min terms, then we will get the corresponding max terms. That is equal to m1 dot m3 dot m5 dot m6. That means in the canonical POS form, this expression can be written as m1 dot m3 dot m5 dot m6. Or in more abbreviated form, it can also be written like this. So in this way, we can convert any canonical SOP form of expression into the equivalent POS form. And if you closely observe, then this POS form contains the number which is not present in the SOP form. That means without the truth table also, we can convert any canonical SOP form into the equivalent POS form, or vice versa, we can convert any canonical POS form into the equivalent SOP form. So to understand that, let us take one more example. So let's say we have been given one expression in the canonical SOP form and we want to find the equivalent POS form. So as you can see, this f2 is the function of 3 variables. That means it will have total 8 minterms and the maxterms starting from 0 to 7. Now in the POS form, we will have the numbers which is not present in the SOP form. So in this case, those numbers are 0, 3, 4 and 7. And therefore, this is the equivalent POS form of expression. So in this way, we can convert any one canonical form into the other canonical form. So similarly, in the next video, we will see that how to convert any non-canonical form into the equivalent canonical form. So we will see that how to convert the non-canonical POS form of expression into the equivalent canonical form, and likewise how to convert the non-canonical SOP form of expression into the equivalent canonical form. But I hope in this video you understood the sum of product and the product of some form of representation of the Boolean expression, and you also understood the concept of minterm and the maxterm. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.